if you look at all the different problems that are out there, all the noise sources, there are generally 6 families of these problems, all based on common elements in the interconnect design. And I'll just mention it really briefly, and then talk about the very important principle about that gives rise to ground bounds. So the first problem, this is the families of signal integrity problems, is all about signal propagating on an interconnect and the self-aggression noise when a reflection occurs. And for those of you that are familiar with these effects, what's the only thing that causes a reflection? An impedance mismatch, exactly right. And so if that's the root cause of the problem, it's all about engineering the impedance the signal sees to minimize those problems. Second family of problems is about mutual aggression. Signal's traveling on one path and it couples over to the other path. In the field's perspective, it couples over by the fringe electric and magnetic fields from one trace to another. And so that says, hey, if you want to fix crosstalk, it's about engineering, sculpting those fringe electric and magnetic fields between one trace and another to minimize the coupling or the field leakage from one to the other. Second problem. Third problem is about, this is the second problem was crosstalk when there was a nice wide return path. The third problem is when the return path is not a nice wide path. And that's where there's still electromagnetic field, and we think about the electric field coupling by capacitance, we think about the magnetic field coupling by inductance. When we have a nice wide path, anybody want to take a guess which is more? When we have a nice wide return path, which is more, capacitive coupling or inductive coupling? Electric field coupling or magnetic field coupling? How many say electric field coupling is more? How many say magnetic field coupling is more? So the answer is, when it's a nice wide path, they're both comparable. They're both equally important. But when we screw up that return path, so it's not a nice wide plane, then the capacitive coupling, yeah, it increases a little bit, but the inductive coupling, the magnetic field coupling, dramatically increases by order of magnitude or more. And that's the environment in which we call ground bounds. It is when we have a screwed up return path, so the crosstalk is dominated by inductive coupling. And that's what we'll talk a little bit more about, because I think it is so important when it comes to layout design rules. The fourth general problem is about losses in the interconnect, and most importantly, it's not the loss per se, it's the frequency dependence of the loss. That in all interconnects, because the fundamental material properties of the dielectric and the conductors, the higher frequency we go, the more the loss is, the more attenuation there is in the interconnect. That means you send a very fast edge down the interconnect with all these high frequency components. The high frequencies get attenuated more than the low frequencies, and you're left with this longer rise time. And as long as your unit interval for the data is short compared to that rise time, hey, no problem. But as the unit interval, as the unit interval is long compared to that rise time, no problem. But as the unit interval shrinks, data rates increase, the rise time becomes longer than the unit interval. The unit interval gets shorter than the rise time, and that means that the bits are distorted, and that's where we get intersymbol interference. And so it's about not the losses per se, but the frequency dependence of the losses. And typical interconnects with given material properties, that happens when unit intervals are in the nanosecond or less kind of time interval, and that corresponds to gigabit and above. And so this is really a gigabit high-speed serial link problem specifically. At lower data rates, hundreds of megabits, it's a who cares. The fifth general family of problems where the interconnect is not transparent is about the power paths. And fundamentally are, again, about connectivity. We're trying to connect the power generators, the voltage regulator modules at one side of the board with the power consumers, the active devices. And for connectivity, we just want to make sure that we can connect the DC voltages to the consumers with acceptable noise. And so you can say, oh, I'm just going to get myself a really great, powerful, wonderful voltage regulator module, stable to 0.1%, and that's going to give me a really good, stable voltage over here. And if the current through the device was constant, then that would probably be the case. But unfortunately, because of the microcode that runs and because of what the chip does, we get these transient currents in the power path, the power rail for the device, and those transient currents through the impedance, not I don't mean to imply the resistance, but the impedance of the power path, those transient currents mean that we're going to get transient voltages. And it's those voltages that cause, the transient voltages that cause all the problems. Here's an example of that. When we have this transient turn-on current in the power rail, we see a lot of transient noise voltage. And while sometimes that can contribute to the eating into the noise margin and creating a bit error by itself, sometimes even if it's not large enough to create a bit error, it will still affect the jitter of any circuits that are part of the clock generation or clock data recovery. And so that voltage noise on the power rails, really important for some specialized applications, anything involved in clock generation, clock distribution, clock recovery, anything that's related to an analog device, either wireless receiver or an A to D or D to A, where voltage noise, where it's very sensitive to voltage noise. And so if that's the problem, transient currents through this impedance giving us a voltage drop, that says, hey, we need to design really low impedances in the power distribution path. And you kind of get the theme here that we translate the problems into electrical terms, and now we have to have a way of thinking about how does the physical design translate to electrical performance. And the last one is where EMI comes in, and there are a number of issues, one of which is very much related to what we're going to talk about next.